So what we can see is this degeneracy. So what we know now is we can start thinking about the next step, because we can fully describe the energy of orbitals, and we can fully describe a complete orbital in terms of its 3 quantum numbers and its 3 positional variables, r, theta, and phi. So next we can think about, okay, what is actually a wave function? And for example, what might the shape of different wave functions be? So essentially what we're asking for here is the physical interpretation of psi, of the value of psi for an electron. And it turns out that the answer to can we have this physical interpretation of thinking about what psi means, the answer is really no, that we can't. There's no classical way to think about what a wave function is. There's no classical analogy that explains, oh, this is what you can kind of picture when you picture a wave function. And that's somewhat inconvenient because we're working with wave functions, but it's a reality that comes out of quantum mechanics often, which is that we're describing a world that is so much different from the world that we observe on a day-to-day basis that we're not always going to be able to make those one-to-one analogies. But luckily, we don't have to worry about how we're going to picture all this now that I said that, because even though there's no physical interpretation for what a wave function is, there is a physical interpretation for what a wave function squared means. So when we talk about a wave function squared, we're taking the square of the wave function, any one that we specify between n, l, and m, at any position that we specify based on r, theta, and phi. And if we go ahead and square that, then what we get is a probability density, and specifically it's the probability of finding an electron in a certain small defined volume away from the nucleus. So it's a probability density. The important point here is it's not just a probability, it's a density, so we know that it's a probability divided by volume. And the person we have to thank for actually giving us this more concrete way to think about what a wave function squared is Max Born here. And actually, after the Schrodinger equation first was put forth, people had a lot of discussions about how is it that we can actually interpret what this wave function means. And a lot of ideas were put forth, and none of them worked out to match up with observations until Max Born here came up with the idea that we just square the wave function, and that's the probability density of finding an electron in a certain defined volume. And it's very helpful because it gives us a way to think about it. We can't actually go ahead and derive this equation of the wave function squared because no one ever derived it. It's just an interpretation, but it's an interpretation that works essentially perfectly. Ever since this was first proposed, there has never been any observations that do not coincide with the idea, that do not match the fact that the probability density is equal to the wave function squared. So also about Max Born, just to give you a little bit of a Trivial Pursuit type knowledge, he not only gave us this relationship between wave functions squared, he also gave us Olivia Newton-John. This is her grandfather. I don't know if you can see from the eyes. I feel like there's a little bit of resemblance there. So I don't know what she grew up hearing about when she went to her grandparents' house, but it might have been wave functions squared. So little tidbit of knowledge for you that's somewhat trivial. Then back to the non-trivial knowledge that is not trivial at all, in fact, is, okay, how do we think about this probability density now that we have a little bit more of an idea? We know that it's a density, it's not an actual probability. So one way we could look at it is by looking at this density dot diagram, where the density of the dots correlates to the probability density. So what you see is near the nucleus, the density is the strongest, the dots are closest together. As you get far away from the nucleus, the dots get farther and farther apart, meaning the probability density at those volumes far away from the nucleus is going to be quite low, eventually going to almost zero, although it turns out that it never goes to exactly zero. So if we're talking about any orbital or any atom, it never actually ends, it never goes to zero, but it turns out the probability is only significant within 1 angstrom. So you can either say that electrons are very, very tiny or that they're never ending, and both are pretty accurate ways to think about what an atom is.